Hi everyone, my name is Linda, and today I will talk about Pandora's problem with non-obligatory inspection, optimal structure, and a PTAS. This is joint work with Beyhaghi, who is currently a postdoc at Carnegie Mellon University. Before we start, we first want to note that another paper that will be presented at the conference, named Pandora Box Problem with Non-Obligatory Inspection, Hardness, and Approximation Scheme, greatly overlaps with us in both results and methodology. Our talk will provide some discussion and comparison with their work, and you can check out their talk videos for more details. We'll start with the motivation of studying the Pandora box problem. In our daily life, we'll often face search problems such as buying a second-hand car or deciding which university to attend. In these scenarios, there are several potential options that the agent would like to investigate. However, investigation of an option such as a used car or your fit at the university may cost money and may be time-consuming. So Weissman formalizes such search problems with inspection cost as the Pandora's box problem. In the Pandora's box problem, there are n boxes, and for each box I, the value in the box is denoted as Vi, drawn from a distribution Di. Note that the distributions are assumed to be independent across items. When the agent inspects a box I, the cost of inspection is noted as Ci and is known upfront. The agent can inspect the boxes in any orders they like, and their goal is to maximize their expected utility, which is equal to the expected value of the box they select minus the sum over their inspection costs. Note that in this model, the agent must inspect a box first before selecting the box. To get a feel for the model, here is a simple example. Let's say the agent inspects the red box first with a cost of 1, and they see that the value of the box is 2. Now the agent can pick any remaining boxes to inspect. Let's say they inspect the blue box next with cost of 2 and find out that the value for it is 8. The agent then decides maybe to investigate this next box, the green box, with a cost of 2, and find out that their value is 7. At this point, the agent becomes disappointed and stops the search process. In this particular instance, the agent gets utility equal to the maximum over their values minus the sum over their inspection cost, which is equal to the maximum between 2, 8, and 7 minus the sum over the cost of 1 plus 2 plus 2. And so the agent's utility in this case is 3. At first glance, it's not even clear that the decision version of the Pandora's box problem is in NP, since the strategy could be adaptive with an exponential number of branches. However, Weissman actually proves that the optimal policy is not only polynomial time computable, but extremely simple and easy to describe. Firstly, for each box, a reservation value can be computed independent of the value of other boxes. Intuitively, the reservation value describes the transition threshold between whether the agent is willing to open the box or not. As an illustration, if the maximum value the agent has seen so far is A, then opening the box has positive marginal utility gain if and only if A is below this reservation value. In the optimal policy for the Pandora's box, which we'll call Weissman's policy from now on, since he is the person who discussed it, the boxes will first be reordered in the decreasing value of this reservation value that we have defined on the previous slide. Then, the searcher will open the boxes in sequential order until the maximum value they have seen so far is greater than the reservation value of all the remaining boxes. Like we have mentioned on the previous slide, reservation value describes the threshold where the agent transitions from gaining positive utility to gaining negative utility from opening the box. Intuitively, for those boxes that have a low reservation value, the agent should defer inspecting them since they may be able to rule out the need to inspect these boxes altogether by having seen a high enough value before. So the study of Pandora's box problem at this point seems pretty complete. We have this clean, greedy policy that is also optimal. However, there is one perhaps a bit artificial aspect of the Pandora's box model, which is that we have to inspect an option in order to select it. In real life, this is not always a constraint. For instance, international students may find campus visits to be too costly and time-consuming, and instead just chooses a university to attend without inspection. This is totally allowed and sometimes what students do in real life. So what if we give the agent the freedom of choice whether they want to inspect the option or not? In fact, many papers have studied different applications and converges on a model that is equivalent to the Pandora's box, but gives the searcher the freedom to take a box without inspection. For instance, Guha Munagala and Saka studies information acquisition in wireless networks. Chown and Liu studies channel probing for spectrum access. PTAS, Crossgammer, Levy, and Shapovsky studies stochastic selection with testing. And finally, Dolfo, modeling the problem as a direct extension of Weissman's model, is motivated by admission applications. And all these papers uses a model that is equivalent to the Pandora's box problem, but where inspection is non-obligatory. And this is exactly the problem we study, which we will formalize on the next slide. So in the Pandora's box with non-obligatory inspection setting, the setup is exactly the same as before, where we have these n boxes and with values drawn from a distribution and costs. And the agent can inspect boxes in any orders they like as before with the same definition of utilities. However, now the agent can choose either to inspect the box or to claim the box closed without inspection. From now on, we will sometimes abbreviate this problem as PNOI for brevity, and this notation is first used in an earlier version of Fu Li and Liu. We just want to note that. So the change from obligatory to non-obligatory inspection doesn't seem significant at first, but actually many things may be different now. Firstly, Weissman's policy is no longer optimal. Let's consider the following example. We have box 1 and box 2, where box 1 has a high variance but a large cost of inspection, and box 2 has low variance but a low cost of inspection. If we calculate the reservation of the boxes, box 1 will have a much higher reservation value compared to box 2. Consequently, in the original Pandora's box problem, with obligatory inspection, the optimal policy is to open box 1 first, and then open box 2 only when the value of box 1 is 0. However, this is no longer optimal for the non-obligatory inspection case. Now, the optimal policy, it turns out to actually be opening box 2 first. And in the case where box 2 has a value of 0, only in this case, we will simply claim box 1 closed without inspection. And only when box 2 has a value of 1 would we open box 1. Observe that in the obligatory inspection case, if we open box 2 first, the value of box 2 is not useful in determining our next actions. We should always open box 1. However, in the non-obligatory inspection case, the value of box 2 actually tells us some information. If the value is 0, then it is not worth it to inspect box 1 since we are going to take whatever was in box 1 anyways, and might as well not pay the inspection cost and claim it closed. On the other hand, if the value is equal to 1, then claiming box 1 closed also only gives us expected value 1, which is the same as what we already have. Therefore, it may be better to open box 1 and take higher value between the two boxes. As we can see, the agent's utility is approximately equal to 1 from Weissman's policy, but close to 5/4 in the optimal policy. In fact, this gap can be made arbitrarily large by a careful construction. So now we have discussed that Weissman's policy is no longer optimal. There are other things that makes the setting seem more complicated than the original setting. For instance, adaptivity may be required for the optimal policy. For instance, consider our previous example, but now we add a third box. This example is first mentioned in Dolvo's paper in 2018. This additional box, which is marked in blue, may give us an extremely high value, 1/epsilon², but with a small probability of epsilon squared, a moderate value of 1 with probability epsilon, and 0 with remaining probability. And so we're not going to go into the details here, but note that the optimal policy in this case is to open box 3 first, actually. And whether it will stop or open box 1 or open box 2 first will depend on what value is in box 3. So this shows adaptivity since whatever box to open next is dependent on the previous value. And actually, a more complicated example will show that the relative position of the boxes in the optimal policy can even change based on what are the other sets of boxes as well. And so no policy of a greedy flavor similar to the Weissman policy will be optimal for the non-obligatory inspection model. Finally, to put a nail in the coffin, Fu Li and Liu proves that finding the optimal policy for our problem is NP-hard. For more detail on the hardness results, please see Fu Li and Liu's talk on their paper that is jointly accepted to STOC this year. So now that we know the problem is NP-hard, the natural next question to ask is the decision version of the non-obligatory inspection problem even in NP? We have observed before that by the natural setting of the problem, the policies may have exponential many decision branches. And to answer this question, we turn to the structure of the optimal policy. If the optimal policy can be efficiently described, then the optimal utility must be efficiently verifiable, which proves that the problem is in NP. There is precedence in proving such structures for NP-hard problems. For instance, for a related problem called free order profit inequality, the details are not super relevant for the talk, but they show that the problem is NP-hard, but at the same time, the optimal policy is non-adaptive. And the hardness mainly stems from choosing this non-adaptive order. So this also shows that their problem is in NP. For our problem, we have no such hope because we have just shown that for our problem, adaptivity is required. However, it turns out that the optimal policy requires limited amount of adaptivity. In our paper, our first main result proves that the optimal policy consists of two phases, where in each phase, the order of visiting the boxes is predetermined and non-adaptive, and we only need to switch the order of inspection once. Note that this result is also proved in Fu Li and Liu using similar methods. We'll start by defining the backup box, which will be integral to the structure of the policy. A backup box in a policy is a box that the policy sometimes claims closed without inspection. For example, in our canonical example that we've seen before with these box 1 with high variance and box 2 with low variance, in the optimal policy, box 1 is sometimes claimed closed when box 2 has a low value. Therefore, box 1 is a backup box. However, box 2 is always opened up front and is not a backup box. As early as 2008, Guha, Munagala, and Sarkar proved a structural theorem that shows that there exists an optimal policy for our problem that has at most one backup box. Now we know that the optimal policy can be described in two steps. Step one is we can choose a backup box, if any. In the case where no backup box is selected, we're basically back in the obligatory inspection case where Weissman's policy is optimal. In step two, we will find the optimal policy given that box I is the unique backup box. So note that even knowing the structural theorem, at this point, we still don't know if the problem is in NP, since a policy that uses unique backup box can still be adaptive and has exponential number of branches. So our main result one shows further structure, where we prove that the optimal policy has the following two-phase structure. First, like we have seen in the structural theorem, we will pick a backup box I star. Then we will fix the initial order and a set of associated thresholds. Note that the thresholds are different from the reservation values defined in the talk before. In phase one, while all the values we have seen are below the thresholds, we will open the boxes in our specified initial order. If we reach the end of the order without seeing any value above threshold, then we will claim the backup box closed without inspection. On the other hand, if we see a value above the threshold, then the policy enters phase two. Once in phase two, we'll actually never claim a backup box closed. In this case, we revert to the obligatory inspection setting, and the optimal action is to run Weissman's policy on all remaining boxes, but with the maximum value seen so far as an outside option. Here's the pseudocode for the two-phase policy. The important thing to note here is that the policy can be described succinctly by the initial order of the boxes and their thresholds. This immediately shows that the decision version of Pandora's box problem with non-obligatory inspection is in NP. In order to prove that there exists a policy that exceeds certain utility, we can simply describe the policy in terms of the initial order and the thresholds and calculate the utility using backward induction. So now we will show a proof sketch of our main result one. Our proof is heavily inspired by Guha, Munagala, and Sarkar and their structural results, but we were able to go a bit further and get a clean structure of the optimal policy. So here we'll give some intuition. Consider optimal policies that uses at most one backup box, like described in the structural theorem. If the policy does not use the backup box, then Weissman's policy is the optimal policy. If the policy does use the backup box, let this box be I star, and consider a sequence of action where at some point we open box J, but even after opening box J and seeing its value Vj, we will still claim the backup box closed with some positive probability. In this case, what we can prove is that if we never see a value greater than Vj in the future, then we will definitely claim the backup box closed. Therefore, either we see a value above Vj in the future, or we will claim the backup box I star closed. And note that in either case, the value of Vj is irrelevant to the final value we select, and because either we will select a value that's above Vj or we will select the backup box. So in fact, in maybe a slightly different optimal policy, we could simply take the same action as when Vj is equal to 0. Now, let tau j be the maximum value of box j, where we still sometimes claim the backup box closed. Then there exists the optimal policy where whenever the value is below tau j, we always take the action as if the value is 0. While if the value is above tau j, then by the definition of tau j, the backup box will never be claimed closed. And we can use Weissman's policy for future boxes. This corresponds to our two-phase policy structure. Now we will discuss our second main result. Using the structure of the optimal policy, we're able to show that there exists a polynomial time approximation scheme, abbreviated as PTAS, for the non-obligatory inspection problem. We'll do this as follows. First, there is a general formulation by Fu, Li, and Liu that shows that certain kinds of stochastic dynamic program has a PTAS. We then restrict our search space to find an approximately optimal two-phase policy. And finally, given this restriction, we reduce our problem to the stochastic dynamic program. Note that Fu, Li, and Liu also provides a p-task for the problem, but with a slightly different reduction that doesn't involve our intermediate step of reducing the search space. Instead, they directly reduce the original formulation that includes all possible policies to the problem of finding the stochastic dynamic program. For the rest of the talk, we will describe our reduction, and you can see Fu, Li, and Liu's video for more detail on their reduction. We'll first introduce the stochastic dynamic program. In the stochastic dynamic program, the agent has an internal value and can take an action at each step. After taking the action, they can get an immediate reward G, and their internal value will be updated. Notice that G is only allowed to depend on the current internal value and action of the agent, and cannot depend on the history. You can think of it as a Markov chain with reward. And at the end of the process, the agent also gets a final reward that is only dependent on the final internal value. The goal of the agent is to maximize their expected total reward, which is the sum of their immediate reward at each step and their final reward H. Fu, Li, and Xu shows that there is a p-task for any stochastic dynamic program that satisfies the following condition. Firstly, the internal value Vi must be monotonically non-decreasing as the time steps increase. Secondly, the value and action space must be of reasonable size that relates to epsilon and sometimes n. Thirdly, the immediate reward G must have expectation greater or equal to 0. And finally, the final reward must always be non-negative. Let's see if we could reduce our problem of finding the best two-phase policy to the stochastic dynamic program. As we have mentioned, the optimal policy and in general the two-phase policy can be described as an initial order combined with the thresholds for these orders. So based on this fact, we can model the agent's action as opening the box with threshold tau in phase 1 and opening the box with the trivial threshold in phase 2. We can model the internal value of the agent as the best value seen so far. And in particular, we can assume that this value is 0 if the value seen is below the threshold, as we have discussed for our two-phase policy. And we can model our immediate reward as our marginal gain in value minus the cost of inspection. And finally, we can view the final reward as getting the backup box expected value of Vi if we never reach phase 2, and getting 0 if we did reach phase 2. Given our formulation, let's see if the conditions for the p-task are satisfied. Firstly, since Vi models the maximum value the agent has seen so far, it is indeed monotonically increasing. However, it is not true that the value and action space are of reasonable size, they're of infinite size. In addition, it's not clear if the immediate reward has expectation greater or equal to 0 for all possible action. Things like this immediate reward has these positive terms of gain in the internal value, but it also has a negative term in terms of cost. Finally, the final reward, which is either 0 or the expected value of the backup box, is indeed non-negative. So corresponding to these two conditions that we've seen that are not necessarily satisfied by our vanilla attempt at a reduction, we have two challenges. Challenge 1 is the negative term in the reward functions that reflects the cost. Our solution to this is to reduce the problem of finding the optimal two-phase policy to an equivalent problem without cost by observing additional structures. Our second challenge is that the value space is too large to discretize in reasonable increments. Reasonable increments meaning that discretize in, let's say, opt over epsilon increments. To overcome this, we first show that if we fix the initial order of the boxes, we can discretize the values to a small set of size polynomial in 1 over epsilon. And then, of course, we don't know what should be the correct initial order, but we show that there's only polynomial in terms of epsilon number when we assume epsilon is a constant, possible small sets of discretizations. And we can try all of them and remain in the polynomial time constraint. Note that although Fu, Li, and Liu uses a different reduction, they also managed to overcome these two challenges using similar observations. So in conclusion, we show that a simple two-phase structure of the optimal policy and provide a PTAS for the non-obligatory inspection problem. There are still many interesting questions to ask in the Pandora's box model, some of which are already in the process of being studied. For example, does there exist a fully polynomial time approximation scheme for the problem? And what happens when the cost is not additive, or if we allow selection of multiple boxes subject to feasibility constraints? Or could we model the fact that we can over-inspect an option in different ways and not just either inspect or not inspect? Or what would be the effect of risk aversion on the Pandora's box problem? We are excited to learn about the answers to all these questions. Thank you for listening.